Hello, my name is Volodymyr, and me and Anton together are a part of an Eastern Bloc team.
Hello, I'm Anton, and this is our attempt to make sense out of the models and discuss their life after the leaderboard score chasing. As you guys did a good job covering the basics of the dataset, we'll jump over to describing our approach to both of the challenges. Let's talk about the modeling approach now. In the quantitative part of the challenge, we need to solve two problems: build a regression model for well's initial production rate, and build a classifier that can decide whether a well was labeled as abandoned, suspended, or active. Let's start with regression. In the simplest example of multivariable regression, we would like to find an equation that expresses our target, in this IP in this case, as a linear function of variables we are provided, such as completions, geological variables, and others. The coefficients alpha in front of each variable is what a computer needs to find using ground truth information provided, that is, a dataset with the real production numbers. A next step further would be to recognize that a relationship between IPs and captured variables might be complex and nonlinear. In that case, we would like to find a function f that is in some way relates our input variables to the target, and we can call that a black box, which we will try to open later. For classification, the situation is very similar. However, instead of IPs, our target now is the probability of a well to be labeled as abandoned, suspended, or active. Our cyclical modeling approach started with analyzing input features and target and determined variables that should provide higher or lower predictive power. We then used domain expertise to come up with the new features and transform the target appropriately. We then trained a model, analyzed residuals and feature importance, and then repeated the process with a few adjustments informed by this analysis. We also noticed that neither geo nor completion variables were present in the dataset, hence we came up with proxies for them using dates, location, and other variables. Specifically, a spot date is a good tracker for the historic trends in max BOE that is likely caused by historically increasing proppant and well length values in the area and tend to have a strong influence on well's performance. On-target transform. Well IP's distribution have long tails, much like rainfall or earthquake magnitudes, which will cause problems when trained on IP values as is. The explanation is here. Therefore, we resolve this problem by switching to logarithm of the target. For classification, no target transform was necessary. However, a problem with the classification is that the balance of classes is time dependent. Obviously, when a field is in early development, none of the wells are abandoned, and vice versa. When a field is really old with no activity, then most of the wells will be abandoned. Therefore, the model trained on a random sample over time will have very questionable forecasting abilities. An important note: for the model to be useful in practice, it should be trained in a reality-reflecting scenario. That is, if the data has a temporary character, for example, spot data of the real test data is only increasing together with the other features potential, the cross-validation technique employed should reflect that. It should not be a simple random split. Moreover, wells are not drilled in a random pattern in time and space. E&P companies tend to develop areas economical at a given time price of commodity. For both regression and classification, our model was an ensemble of gradient-boosted trees. Its light GBM implementation benefits from a highly efficient C++ backbone code that makes it a great candidate for quick experimentation. We then trained a model and looked at residual plots to identify samples of higher errors for further analyses. Naturally, we would like to know which features our model identifies as more important, so we use SHAP package to estimate and visualize importances. For regression, this plot shows features in the order of decreasing importance. Max BE is a top feature due to the fact that it obviously leaks the target. That is, it's strongly correlated to the target values, however is not available in the reality. We simply do not know max BOE prior to drilling, much like IP. Among other strong features are obviously the location of the well, lat and long, which maps the rock quality and geological features, and its vintage, spot date that most likely maps completions features. Similar to regression, features for classification are shown here in the order of decreasing importance and their impact on the particular class probability, shown by a colored bar. A brief examination of the feature importance plot and the probability dependency plots for each of the class may help understand how a model makes a decision. For example, non-NA max BOE suggests that a well is still active, most likely because the number is available for later spot date wells. The closer time difference between a surf abandoned date and a status date is to 0, the more likely that a well is abandoned. There's no more status updates after a well is abandoned indeed. For some operators, which corresponds to certain values in current operator parent feature, the game of drilling in the Viking Basin is over, as you might see by the elevated chances of wells being abandoned if they belong to those operators. Finally, a few quick notes on the future usability of the models. For regression, high-scoring models rely heavily on max BOE, and we are afraid there is not much practical use, as max BOE is not available at the time when IP prediction is desired. However, if max BOE was to be eliminated and some completions geology data was added, then a similar modeling procedure could be used in evaluating reserves and impact on production caused by various completions practices. From a risk point of view, one could apply this model in a step-off or clustered manner and identify geographic area zones where predictions are less reliable. Example is given here. Less reliable areas could be loosely defined as those characterized with high error in predictions. Those areas can be then marked as risky and could be given a higher discount when economical analysis is performed. And then in classification, similar to regression, the models that score high in this competition are quite useless since they directly use leaking proxies for the target, such as surf abandon date. If that feature was to be eliminated, then the model ends up relying on an operator and their historical activity in the region. We're still facing a problem of a model having no predict in the future capabilities, since the dataset in its current form is rather static, such as none of the columns are time dependent. However, if the dataset had time dependent features, for example, days since a closure event or days in production in the last year, it would be interesting to develop a model that predicts days till abandonment. We could get the probabilities of a well to be abandoned in the next n months. The main value here is to have this probability change over time, thus allowing the user to quickly identify areas where a large population is likely to be abandoned.